as well. All right, let's get into it. So topic 1 is loans and investments. So we're talking about money. When we're talking about loans and investments, we're really just talking about money. So my first little connection that I have to prior knowledge to make that link for you today is geometric sequences. Hopefully it hasn't fallen out of your brain too much and you remember studying geometric sequences in Unit 3, which would have been probably a few months ago. So geometric sequences is where we take a starting point and then we multiply it by a constant factor, which when we're talking about geometric sequences, that's r, and then we take our new term and do the same. So we take our starting point, which for example could be the number 3, and then we multiply it by a constant factor, which could be the number 2, for example. So we take our starting point, 3, multiply it by 2 and get 6, and then we times that by 2 again and get 12, times that by 2 again and get 24, and it can go on and on and on and on because it's a sequence. So we're just applying the same rule repeatedly. And the good news that I have for you today is that compound interest is essentially a special application of geometric sequences. So we're actually doing quite a similar thing if you think about it conceptually when we're doing a compound interest, because we're taking a starting point, which would be the amount of money in the investment or the loan, and then we're multiplying it by a constant factor, which is the amount of interest being paid or owed, depending on whether it's a loan or an investment. And then just like in our geometric sequences, our number grows exponentially as it's multiplied by the constant factor. The same happens in our loans and investments because the sum grows over time. So for example, you think about superannuation. The reason money is put aside into superannuation accounts and set aside for retirement is that, or the reason that people choose particular funds to trust their money with, is that hopefully compound interest will be being applied to that money so that the sum in that account can grow, as well as the contributions being made by a person's employer. Same might occur in like a long-term or like a savings account, or also if somebody has a mortgage or a house loan, there's always going to be this compound interest at play. So we're going to be talking about that a little bit more today to hopefully either revise it or further develop your understanding of that a little bit more. So just like with sequences and with simple interest and with compound interest, we can calculate it using a recursive definition. So the idea of recursive is when we take the starting point and then we apply the same rule to get our second term, and then we apply the same rule to get our third term, and then we go on and on in that fashion. And the rule that we use to do that in the case of compound interest is n plus 1 is equal to r multiplied by an, where a0 is the initial quantity. So if, for example, someone invested $2,000 into a bank account, then $2,000 would be A0 because that's the initial starting point of the money. AN is the amount owed after n periods, or the amount made if it's an investment. Because again, this can apply to both a loan or an investment, because in an investment, the amount of money that you personally have is growing, but in a loan, the amount of money that you owe is increasing because interest is being charged on the money that you've borrowed. So AN, the amount owed after n periods, and then R is our rate of interest. It's like the factor by which the amount of money is growing by each period, and that we can calculate that by saying R equals 1 plus I over M. And I want you to take note of this carefully because some textbooks might define this as like X over M or X over I or K over T. There's all these different variables that different like textbooks and courses and structures and programs use to define this. So the important thing isn't to memorize the letters. The important thing is to actually know what the letters represent, so that if you are given this formula or if you memorize this formula, you actually know how to use it. You're not just writing down letters that you actually don't know what they represent. So a better way to think of this rather than I over M would be R equals 1 plus the decimal interest rate per annum divided by the number of compounds per year. So when we're talking about the decimal interest rate per annum is referring to yearly. And when we're talking about decimal, that means like in decimal form. So if the interest rate on a loan or investment was 5% per annum, then we'd say 0.05 divided by the number of compounds per year. And if it's compounding annually, then there's 1 compound per year. If it's compounding monthly, then we have 12 compounds per year. If it's compounding weekly, we have 52 compounds per year. So those are kind of the different ways that we define the variables. So let's do an example to hopefully make that a bit clearer. So let's say we invested $1,000, which should be our starting value, at 5% per annum, that should say, per annum, compounding annually for 2 years. So we'll start filling in and labeling our variables to work out what we know and how we can get our answer. So A0, our starting point, like I said, is $1,000. And AN is the quantity after N periods, which in this case is our unknown. So AN is like the variable that we're trying to find. And R, like we said, it's the decimal interest rate divided by the number of compounds per year. And here, our decimal interest rate is 5% per annum. So we've taken that, turned it into a decimal. So we've got 0.05, and we have 1 compound per year because it's compounding annually. So our M is 1. And we want to make sure that we're adding 1 as well. So our R, which is the rate by which our loan is growing, is 1.05. And next, that's all we've been able to define. So now we start by just like solving the formula and working out what the value is after 2 years. So to do that, the first thing we'd say is let n equal 0. So what we'd do, we'd take this formula here, say let n equal 0. So then we'd have a 0 plus 1. So that would give us a1 is equal to r multiplied by A0, our starting point. So that's what we've done here, A1, so the amount after 1 period, the amount after 1 year, in this case, is equal to 1.05, the factor by which it's growing, multiplied by the amount that we had to start with, which is, in this case, $1,000. And that gives us $1,050. So here we can see that the quantity after 1 year is $1,050. But we're being asked what's the quantity after 2 years. So then we've got to apply our recursive rule again. So we'll say let n equal 1. So now we're saying A2 is equal to R times A1, which makes sense because we're applying the rule to the following year. So we're saying, well, how much would there be after 2 years? And we can work that out because we know how much was there after 1 year. So we'd say the amount after 2 years is equal to the amount at the end of the 1 year and then multiplied by the same factor because it's growing by that same amount. And that'll give us $1,102.50. And you'll notice that here we made $50, but here we actually made $52.50. So you'll see that we actually made a little bit more money the second time around. And it would be the same if we kept applying the rule. Each time we'd be making a little bit more money. And that's the whole idea of compound interest, because that's kind of the differentiating factor between simple interest. Simple interest could be modeled by arithmetic sequences, because simple interest is that scenario where we're adding the exact same amount every time. We're getting $50 interest every time. So it would form that linear pattern. But when we're talking about our compound interest, we're modeling that kind of in a very similar manner to geometric sequences. You can see that it's actually growing by a little bit more each time because we're applying our rate of growth to the previous new amount. So the amount of interest or the amount of money that we're earning interest on is growing. So the amount of interest we're earning is growing as well because interest is based off like a percentage. So that's the really cool thing about compound interest. But what if we invested $1,000 at 6% per annum for 2 years? So the difference here in this scenario is in our last question, we were looking at what if we invested at 5% per annum. But here we're asking, but what if we invested at 6% per annum? So we'll do the same thing. We'll work out our formula. Our starting point is still $1,000. We still don't know AN. The goal is still to find out how much money we'll have after 2 years. But here R is a little bit different. Our decimal rate of interest is 0.06 instead of 0.05, because now we've got 6% per annum instead of 5% per annum. So the money that we have in that compound interest loan or investment is growing by 6% every year rather than 5%. So it's going to be growing more each year. And when we get our answer, that'll illustrate that. So again, we'll say let n equal 0. So the amount of money after 1 year will be equal to our starting value multiplied by the factor that it's growing at. And that'll give us $1,060. And you can already see that we're already $10 better off. And then we apply the same to find out how much after 2 years. We take our new value, 1,060, and we're multiplying it by 1.06. And you can see that now we've made we have a total of 1,123.60, which we can see is quite a bit more than when we were only calculating at 5% per annum. So you can see it's quite beneficial. If we had an investment, we would actually want a higher rate of interest, because that would mean we would be earning more money. But the interesting thing is, if it's a loan, we would actually want the lower rate of interest, because we don't want to be paying interest. We want to be paying as little interest as possible. But if it was an investment, then to choose the option that would work best for us, we would want to choose the higher rate of interest option. So that's an interesting thing to think about. Okay, so now we're going to have a look at another scenario. So what if we invested $1,000 at 6% per annum, but what if it compounded monthly? So before we had yearly compound, so our loan or investment only compounded once a year. Well, here we're talking about an investment. But now we're looking at a scenario where what if it actually compounded monthly? So again, we'll take the same formula. We have the same starting point. We have the same end goal. We want to find out how much money are we going to have in our investment after 2 whole years. But here, again, is where we have another slight change in how we find R. So R is no longer telling us how much our money grows by every year. It's telling us by what factor does our money grow by every month, because now we're looking at monthly compounds. So I is the same as in our last question. It's our decimal rate of interest, 0.06, because we've got 6% per annum. But the interesting difference here is that now instead of 1, we have 12. Because M, if we remember, was referring to the number of compounds per year. And if it's compounding monthly, then we're going to have 12 compounds per year. So R, the rate by which our investment is growing every month, is 1.005, which is a smaller number. Oh, sorry, that's my mistake there. That should be 1.006 because it's divided by 12. Yes, sorry, 1.005. My bad, that is correct. So it's growing by 1.005 every month, which is a smaller number than with 1.06, which is what we were looking at before. But now we're kind of wondering, well, before when it was 1.06, that was only compounding once a year. But this 1.005 is going to compound 12 times a year. So I wonder which one's going to give us the better outcome. And let's have a look at it. So when we're looking at monthly compounds, recursion is going to take a little bit longer because we need to look at the compound for every single month. So let n equal 0. So here we have A1, and because we're not looking at yearly time periods anymore, we're looking at monthly time periods. Here we're saying the amount after 1 month will equal to $1,000 multiplied by our growth factor, 1.005. So we're going to have $1,005 after 1 month. And then if we say let n equal 2, then it'll be A, 1 plus 1. So A2, the amount after 2 months, will be equal to $1,005 multiplied by 1.005. And that will give us $1,010 and 0.025 cents. So you can see that our amount is starting to grow bit by bit. And then the amount after 3 months will be about $1,015. The amount after 12 months, so the amount after 1 year, will be $1,061 and about 68 cents. Then if we keep going, the amount after 24 months, which we know is 2 years, will be $1,127.16. Instead of when we did annual compounds, it was only $1,123.60. So we've made about $4 extra over the 2 years. And that's definitely not a whole lot of money, but it does illustrate the fact that more regular compounds mean we actually earn more money overall because it's compounding more frequently. So, and you can definitely think about or imagine like how much of an impact that would make if we had a time period of longer than 2 years, or if we had an amount over like more than $1,000. So for example, a home loan, for example, of like $500,000, whether it compounds monthly or annually, could make a really big difference to how much we owe at the end of the time period. So here are a few of the takeaways from those examples that we looked at. So when we increase the interest rate, the amount will also increase, because when the interest rate goes up, more interest is being applied, so the amount is going to grow quicker. And also, when we increase the number of compounding periods, the amount will also increase. So if it compounds once per year, compared to if it compounds 12 times per year, compounding more times per year, so for example, the 12 times per year, that means the amount will increase more. So like I said, it's like if we're increasing the number of times our money compounds, that's how it kind of equates to increasing the amount of money that we do get from that. And this is what I said before, and this is a very, very important thing to take note of, and something that's going to be really, really important in a lot of the questions that you get asked. So whether you want a higher or lower interest rate, or whether you want more or less compounds per year, depends entirely on whether it's a loan or an investment. Because in either scenario, we're going to want to make the choice and choose the option that works financially best for us. So if it's a loan, we are going to want a lower interest and less frequent compounding periods, so we're not paying as much in interest. But if it's an investment, we are going to want a higher rate of interest and more frequent compounding periods so that we're actually earning more money off our investment. So if you're asked a question about should somebody choose 5% interest or 7% interest, for example, the first thing you should be thinking of, well, is it a loan or is it an investment? Because that is entirely and 100% going to influence whether they choose the 5% or the 7%. So it depends on whether it's a loan or an investment, because we're always going to want the best option financially for yourself or the person in the question, depending on whether it's a loan or an investment.